Hello students. Uh, Today we will discuss about the design of flat V-belt and chain drive. So initially just take a look out of a PSG where these designs are available. Okay. So referring PSG page number 7.52. So the basic information about the type of belt, flat belt, then basic specification with based on the number of plies, then minimum pulley, then belt length, speed, tension, belt take-up system, then load correction factors, arc of contact. So these are the basic information which is provided over here. Okay, and about the pulley standard dimension, page number 7.55. It starts from 7.54 to 55 and continue with the design of pulley 7.56 and 7.57. Okay, in from PHP page number 7.58, the V design of V build will be start. It starts with the type of cross sections with when we select the proper cross section, we can get a pitch, diameter, as well as the thickness and width of belt. Okay, so few recommended standard normal inside length based on the cross section and their pitch length with correction factors. Okay, so these are the standard data for V build. Here also minimum you can calculate the normal length, then power factor, transmission factor. Okay, so ratings based on uh, the cross section has been shown over here. Okay, so this one, then arc of contact, service factor, correction factor, and this is a number of belts. Okay, now next one, design of chain. So it started from page number 7.71. Normally we are selecting a standard chain, and according to that we will check whether the other parameters are okay or not. So these are the standard parameters where we can see uh, simplex, duplex and triplex chain. The diagram is shown over here. From this to this, there are simplex chains. This one is a duplex and this one is a triplex, where the three number of consecutive sequence of chains are used, or you can say three rows are used. Okay, so similarly here, based on the different type of chain number, here the ISO designations and the roll-on designations also shown over here. So based on that you can find out the pitch, roll diameter, width, pin diameter, plate depth, then translation pitch diameter, overall joint maximum overall over joint maximum value, then bearing area, weight per meter, and braking load. Normally the chain has been selected depend upon the braking load. If nothing is given, okay, assume standard chain, and based on that continue your design. Okay, so let's first start with the flat belt design. Okay, uh, taking a simple example so that it is very easy to understand. Okay, uh, design of flat belt with the pulley. A flat belt drive is to be used to drive a reciprocating compressor running at 720 rpm at 15 kilowatt, 1400 rpm electric motor. Okay, what is given, compressor is running with 720 rpm. Okay, to produce a power of 15 kilowatt, and To drive the compressor, we are using an electrical motor which runs at 1440 rpm. The required center distance is 2 meter. Select a flat belt for a drive from the manufacturer's catalog. The power rating per meter width of the belt per play is 180. Arc of contact and 10 meter per second. Belt speed is 0.028 kilowatt. Okay, this is the value of 0.082 0.023. It is nothing but a power rating. Okay, so you should use this power rating for further calculation. Okay, so capital N is equal to 720, as it is speed of compressor which having a higher diameter pulley, and for lower diameter pulley that we are using, small n is equal to 1440 rpm. Power to be transmitted is 50 kilowatt, 15 kilowatt. Center distance is 2 meter, that is nothing but 2000 millimeter. So first step is to calculate a pulley diameter. Basically, assuming the speed that we have given in PSG, page number 7.53, where the range of the belt speed is given as 17.5 to 22.5 meter per second. Okay, so we are assuming that the belt speed is 19 meter per second. So V is equal to pi dn by 60. So according to that, you can calculate the diameter, small diameter, that is small d is equal to 251.995 mm, as the d is equal to, okay, d is find out on the basis of rpm, that is of 1440 rpm. Second one, select a standard pulley. Okay, the pulley diameter which we have calculated based on the assumed velocity. Okay, now we have to select a standard pulley diameter referring page number 7.54, where the crown type of pulley we are generally referring. Why we are using crown type? Because such a crown type pulley we are using, because of this crown, or you can say a curve, the belt will not be move from the center position, or you can say it will not be slide, or it will not be run out from its working location. Okay, so that's why, and to better grip, we are using such crown type crown type of pulleys. Okay, so standard diameters are given. We have calculated value, that is nothing but 251.995. So when we select recommended diameters with the tolerances, okay, so nearer value is 250. Okay, so that's why we are selecting 250 mm. Otherwise we have to go for 280, and 280 value is very large as compared to the calculated value. So that's why we are selecting the nearest value which we have calculated. Okay, so the standard value of diameter of pulley is equal to 250. Next one, now we have to calculate the diameter of another pulley, that is a pulley from compressor side, that is capital D into capital N is equal to small n into small d. So that ratio, or you can say speed ratio, you can use, and based on the speed ratio you can calculate the diameter, or you can directly calculate the transmission ratio also, n by n divided by output speed divided by input speed. So you can get a transmission ratio, and based on that transmission ratio also you can calculate the divided value of capital D. So we are using similar equation, n by n divided by small d divided by capital D. Putting all the values, what we get, the capital D is equal to 500 millimeter. Now calculating, next step, calculating the correct belt speed. Okay, as the diameter which we have calculated was 251 point something. Okay, now but we selected from standard catalog is 250. As the dimension changes, obviously there is a change in velocity. Okay, now we are calculating the standard velocity based on this diameter. So putting the diameter d is equal to 250, small n is equal to 1440 rpm, calculating the actual velocity, that is a 18.85 meter per second. Okay, so this one is a actual velocity. We was assumed 19 meter per second, but in actual practices it is found this much. Next step, calculation of load correction factor. So based on the PhD page number 7.53, load correction factor is provided over here. Now based on the application, which application we have application of reciprocating compressor. So here you can select the compressors over here. So the load factor is 1.3. Okay, look at here. Here the load correction factor is shown. Okay, out of based on the our application is a reciprocating pump or a compressor type. So this one is over here, that is a intermediate load, and the value of correction factor is 1.3. Okay, so calculating the design power is equal to correction factor into the power given power. So 1.3 multiplied by 15, what we get, that is 19.5 kilowatt. Next step, to calculate the arc of contact. Normally arc of contact alpha is equal to sine inverse of d minus d divided by 2c divided. Okay, so where capital diameter 500 minus small diameter 250 divided by 2c, that is 2 into 2000. Okay, similarly you can directly find out this value by using equation from PSG. Okay, referring PSG page number 7.54, here the equation is directly given. You can using same equation formula, that is arc of contact is equal to 180 degree minus d by d divided by c into 60 degree. Okay, so putting all the values, you can directly get the values which we have calculated over here through this equation. Okay, so you can you can calculate from both way, from this way also, and using PSG equation also. Okay, so here I'm just simplifying that equation, and according to I have designed. So the arc of contact which we have calculated is 172.83 degree. Okay, now we need to calculate arc of contact correction factor. So referring PSG 7.54, so here the arc of correction factors are given accordingly. We have the value is in between 170 and 180. Okay, our value of arc of contact is 172.83, which is lies in between 170 and 180. So by using interpolation method, we can calculate the value. Okay, so using interpolation method, we have calculated, that is a arc of contact correction value, FD is equal to 1.0286. Okay, next one, the modified power rating. So the calculate to calculate the modified power rating, as the velocity it has been changed and we need to consider a correction factor based on the arc of contact. So equation is given over here. Modified power rating per width of the belt per ply is equal to given power rating per width of belt per ply divided by correction factor multiplied by velocity divided by 10. Okay, so putting all the values, what we get, the modified correction factor, modified power rating factor, power rating per width of the belt per ply is equal to 0.04215 kilowatt. Okay, which we are using for further calculation. Now next one, to calculate the belt width multiplied by power, number of plies. That equation we can calculate, or multiplication value of we can calculate by using PhD page number 7.54. Here the equation is given. Okay, so using this equation you can calculate the value, or you can say multiplier factor of width multiplied by number of plies of the belt. Okay, so based on this you can calculate this ratio, so that we can calculate the other parameters. So it is equal to width into number of plies is equal to corrected load divided by load rating per per, or you can say modified load rating per per ply at the build speed. So PD divided by kW modified, so 19.5 divided by 0.04215. So what we get, the width and number of plies is equal to 462.63. So that constant we get. So the width is equal to 462.63 divided by number of plies. Now we have to select a standard value of number of plies as well as the width. Okay, so using this equation we can calculate the belt width. Okay, for number of plies, if you're referring PhD page number 7.52, okay, here the specification of standard plies and the width of belt has been shown. Okay, so for 3, the maximum number of plies up to the 125 to 100. For 4, you can use ranging between 25 to 200. For 5, it is between 76 to 250. For 6, it is ranging between 100 to 250, and for 8 it is in between 200 to 400. Now we have to find out the width based on the equation, okay, which we have already calculated in between number of plies and the width ratio. Okay, so if you selected number of plies is equal to 3, then B is equal to 462.63 divided by 3 is 154.21. Okay, when we look, or when we check in the number of plies 3, there is no such values available, so we can escape this value. Okay, so first of all, look at we will check for values of belt width based on the number of plies. Now select number of plies is equal to 4, then what we get, belt width is equal to 115.66. when we consider number of plies is equal to 5, B is equal to 92.52. when we use number of plies is equal to 6, then the value of B is equal to 77.105 mm. Now out of this we have to select a proper value of B. Okay, so when we refer the values, okay, for 6 it is ranging start from 100, but in case of calculated value of uh, 5 plies. It is ranging in between, it is calculated value is 92.70, sorry, 92.52, which is nearer to the 100. So that's why, as we found that the total calculated value out of the one for plies, number of plies 3, 4, 5, 6, the better value is for number of plies are 5 and the width is equal to 100. Okay, so we have selected. Next one, calculating the length of belt. So referring PhD page number 7.53, you get equation. Here the belt length is given. Equations are given for open drive, cross drive and quarter turn drive. So we are using, in our case, it is open drive. That's why we are using this equation. L is equal to 2C plus pi by 2 D plus D plus D minus D divided bracket square divided by 4C. Okay, here L is the length of belt, capital D is the diameter of larger pulley, small d is the diameter of smaller pulley, and C is the distance. Now let's see the exact calculated value. Okay, so the putting all the values in the proper in the equation, what we get, the length L is equal to 5186 mm. Okay, so now next one, calculating the belt tension. Now this belt tension we are using for pulley design. Okay, so other parameters of pulley, what we have to design, that is number of arms, then cross section of arm. So that's why we needed a belt tension. Okay, so belt tension P is equal to, sorry, P is equal to F1 minus F2. You can denote also T1 minus T2 also. So it's depend what nomenclature we are using. So here F1 minus F2 into V divided by 1000. So putting the values, what we get, F1 minus F2, both are unknown factors. So that's why we are selecting the empirical relation that F1 is equal to twice F2. Okay, now putting this empirical relation instead of F1, that is twice F2, what we get, F2 is equal to 1034.48 Newton and F1 is equal to 2068.96 Newton. So when we calculating the torque T is equal to F1 minus F2 divided by 2, that is the average belt tension multiplied by diameter. Okay, so T is equal to 258.62 Newton meter. Next one, calculating the width of belt. So belt width is equal to 1.25 times of belt width of belt. Okay, sorry, when we calculating the width of pulley, that is equal to 1.25 times of width of belt. So, because we are using some excessive space, because whenever there is a possibility of, due to the fluctuation or vibration in the mechanism, it could be slide, or you can say axial movement can be occur, and to avoid the sudden slip, or you can say sudden failure, we are using some space of you can say width of pulley must be greater than that of the width of belt. Now next one, that belt width which was we calculated is 125 mm. Next one, to calculate the thickness of rim of the pulley. So here we have drawn a cross-sectional view where the outer force diameter of, or you can say maximum tension, is applied at the particular distance, that is a capital R minus RB, that is the distance. Okay, at that distance the total maximum torque is applied, that T is equal to N into R, where capital N is equal to number of rims. Okay, so here we are using cross section of rim is elliptical, which is nearer to the housing, or you can say hub, shaft hub. Okay, now let's how we can calculate. So T is equal to D by 300 plus 3, referring page number 7.57. So the thickness, or you can say the thickness of the rim is equal to 5 mm. Now next one, to calculate the number of arms on pulley. So that is N is equal to 1.7 square root of D by 100. So putting all the values, what we get, N is equal to 4. But from PSG, we can find out that the number of arms is equal to 4 for pulley diameter up to the 450 mm, and the number of arms is equal to 6 for diameter of pulley over the 450, and our diameter of pulley is 500, so that we have selected this one, that is number of arms is equal to 6 as the value of pulley, or you can say diameter of the pulley is exceed or over than 450, and it can be increase the beam strength. Okay, so that's why I've selected number of arms as equal to B, sorry 6. Next one, calculating the dimensions of arm cross section. As we know, we have selected elliptical type of cross section. Okay, so the radius of hub RB is equal to twice of R, or you can say D is equal to D, that is a 35 mm, which we have assumed that the diameter of shaft is equal to 35 mm. Radius of rim capital R is equal to D by 2, that is 500 divided by 2. It's nothing but 250 mm, or you can say 0.25 meter. The maximum bending moment acting on the arm at the hub end, that is M is equal to torque into bracket R minus RB divided by NA, where is the number of arms into capital R. So putting all the values, what we get, the maximum bending moment MB is equal to 37.068 Newton mm. So generally the pulleys are made up of cast. So here we are considering the more factor of safety. The bending stress we have considered is equal to 15 Newton per mm square. Okay, the sigma b is equal to m by z. So we don't have the value of z, so that's why we are calculating directly the value of z first, because we know the value of sigma b and m. So the polar moment of inertia zb is equal to 2.4712 into 10 raised to minus 3 mm cube. Okay, so we are, as we are using elliptical cross sectional area, the empirical relation between the width and the length is equal to, or you can say thickness, thickness not, A. If you look at over here, okay, the width which we have considered as V1, and the length which we have considered, or you can say vertical dimension which we have considered as a A1. Okay, so the empirical relation between A1 and B1 is equal to, A1 is equal to twice of B1. Okay, so using same empirical relation, ZB is equal to pi by 32 into A1 square into B1, as A1 is equal to twice of B1. Putting all the values, what we get, B1 is equal to 18.46 mm, which is approximately equals to 19 mm. Okay, so B1 is equal to 19 mm, as the A1 is equal to 38 mm. So the major axis of the arm cross section at the hub end A1 is equal to 38 mm, and the minor axis of the arm cross section at the hub end B1 is equal to 19 mm. So this way you can calculate the parameters of flat belt drive, as well as you can design a pulley. Okay, where we can use normally the pulleys are designed for maximum bending stress. Okay, as the arms are number of arms are increases, there is a less chance of failure for bending stress can be occurred. Okay,